everyone, welcome to the Weekly Space Hangout for Friday, February 26th, 2016. I'm Fraser Cain, publisher of Universe Today. This week we've got some crazy stories. We're going to be talking about fast radio bursts, the search for Planet 9, WFIRST, double shadow transit season 2016 is on. What's happening this week in Musk? The Pulsar web searching for gravitational waves. Nicole is going to squee about fast radio bursts, which is going to be wildly entertaining. Milky Way survey, getting to Mars in 3 days. And Scott Kelly, it's time for him to come home. Joining us this week, we've got Dave Dickinson. Hey, David.
Hey, still here in Norfolk trying to fly out to Spain.
Oh. Are you spending more in hotel bills than the savings would be on flight?
Not really, because we live on the road long term, so we got to put a roof over our head. Of course,
no matter where you are.
It's a little more expensive here in the U.S. than it would be over in Spain to put a roof over our head. So not extremely expensive, but so it's we've got plenty of time to burn, but we do want to get over there. I think there is 3 flights over the next 4 days. I think we're going to be out of here by Tuesday.
Yeah. We got Jolene Creighton. Jolene,
hello.
How's it going?
Not too shabby. I have my lower third this week. I got coffee, so things are going well.
And you have this dreamy background. It feels like we're under the sea or something.
It is.
Yeah.
Should I sing like Little Mermaid or something? Is that a thing I should do?
Please do.
If you want, we'll wait.
Under the sea.
I'll join.
Under the sea.
Oh, totally called my bluff. All right, we got Kimberly Cartier. Kimberly.
Hi, Fraser. Hello, viewers.
And we've got Professor Nicole Gugliucci. Long-time viewer. For those who have no idea who Nicole is, for a while there, Nicole was the host of the Weekly Space Hangout. I'm really just filling her.
I forgot about that.
Yeah, you used to do the Weekly Space Hangout. We used to take turns. Yeah, so I'm really your replacement. Boss.
Well, but I was your replacement first, so you just took it back.
That's true. Yeah. It was too much fun. I couldn't resist.
You couldn't say.
You know what happened was, we started it. I hosted it, and then I was like, "This is killing me."
Yeah.
And you were like, "No, it's important. We'll keep doing it."
I'll wrangle the cats.
I'll wrangle the cats. And so then you started doing it, and then you sort of made all of the madness settle down until I'm like, "Wait a minute. That doesn't look so awful anymore." And so I jumped back in with appropriate assistance. So your invaluable job was to make it not an overwhelming cat herding nightmare. So thank you.
Thank you.
Yeah. Oh yeah, you're the cat herder supreme. Right. So just want to remind everybody, this is a live interactive show. So if you're watching this right now and you want to talk to us, ask us questions, just comment with the rest of the fans, you can do so. And the way you do that, and I apologize that this is complicated, is that you have to go to the YouTube channel, to our live, to the Universe Today or the Fraser Cain YouTube channel, and then wherever the live video is, there is a link to chat with people. You can pop it out into its own separate little creature, and you can say hi there. So, and that's why I said hello to everybody. Wow. So many people. Yeah, Scott Lewis. Guido's saying that Scott Lewis also did some co-hosting of the Weekly Space Hangout too. And we had poor Amy share a title host one time.
Yeah, I was there.
Yeah, that was fun.
It was.
So it doesn't have to be me. It could be lots of people can host this thing.
I remember I hosted once for like a coffee shop.
Yeah, I remember you did it with the coffee grinder going off there.
In the background. Yeah, you basically took over the show because I was like, I'm useless, guys. There's no internet at home.
I'm a bad host, yeah. All right, well, let's move on. So I'm going to pick some stories at random. Not at random. That really intrigued me. Okay, tell you what, Nicole, let's start with you. You are our special guest, as it were, today. So can you tell us what's going on with fast radio bursts? A discovery you think is more important than almost anything?
Actually, I'm going to hand this over to Kim because she had some cool stuff about it. I was going to back her up with...
Okay. So Kimberly, you set it up, and then Nicole, you can just freak out in the background.
Okay.
Yeah, I was going to make sure, Nicole, that you had a chance to properly freak out about this amazing, amazing discovery that happened. We were chatting before, and we were saying this is on the same level as the gravitational wave discovery a few weeks ago, but it's one that a lot fewer people have actually heard of. It's called fast radio bursts, and what it does is it solves one of the outstanding problems with our current understanding of cosmology, which is the missing baryon problem. So for some context there, fast radio bursts are extremely short-lived, completely unrepeated events that are ginormous bursts of radioactivity from galaxies far, far away. And before this, there had only been about 16 of them actually ever measured, and we could never get to them fast enough to do follow-up observations to figure out where they came from, what could possibly have caused them, because they would happen randomly and we'd find them months later in our data. But recently, a team down in Australia was able to catch one of these fast radio bursts almost immediately after it happened using a rapid response network, and were able to get multiple telescopes pointed at the area of the burst within hours of this event, and were able to pinpoint where it came from and determine what likely caused it. And when you do that, you can get a distance to this object, which is a distant elliptical galaxy, and from that, they can actually get a measure of how much intergalactic material this burst had to travel through in order to get to us. Now, this is a very important thing to measure. We don't get to do it very often, but we need to be able to measure the density of material in the universe that we cannot visibly see, but is still made of normal, regular baryons. For those who may not be aware, the existing commonly held model of the universe says that there is 70% dark energy, 25% dark matter, and a measly 5% of baryonic matter, which makes up all of the normal stuff. But only about half of that baryonic matter had ever actually been seen, leaving 2.5% of the universe completely just missing. We had no idea where it was. We couldn't find it. We couldn't measure it. But now that we have been able to measure this fast radio burst immediately after it happened and trace its path through the universe, we can actually measure the density of this unseen material. And what we have found is that the density of material that this burst has passed through has completely made up this baryon deficit that we had. So all of these missing baryons that put a lot of doubt onto the current cosmological model, it's been found, it's been fixed, and it just puts another measure of confidence in the dark energy, dark matter idea that we have. It's very exciting.
Okay, cue up Nicole.
Cue up Nicole!
So
Yes,
right,
yes.
so I mean, this is. I mean, I know we've reported tons on this with the universe today. That the big mystery is where's all this matter, even the regular stuff. So now we have been able to measure the density, and it matches the predictions as described.
Yeah.
So what is it?
It's diffuse plasma in the intergalactic medium.
So
And
it's just like hydrogen gas
Electrons
out there.
and
electrons,
Perfect,
hydrogen, plasma, which is incredibly difficult to actually measure unless you can track one of like a radio burst or a gamma ray burst through as it travels through the plasma and disperses into all the different frequencies.
Yeah, this is a similar technique that's used in pulsars for determining how much ionized material there is in the galaxy between us and a pulsar. When you have a short radio burst that happens over a wide range of frequencies, the speed at which it moves through a charged medium, so something made of electrons and protons, for example, differs depending on what wavelength it's out. So by measuring the frequency or the wavelength and what time they hit our telescopes, you can say, oh, there's this much material in between. Now, you could do that with fast radio bursts for a while, but without actually knowing the distance. There's this much material, but how big of a space is it taking up? The fact that they were able to get on sky and catch the afterglow so quickly is the amazing part that put that piece in.
Yeah, it's getting the distance to that galaxy that really solves that problem, so you can get a density of material.
Yeah.
And, I mean, like, there was a possibility that it could have been far more massive than people thought, right? Like, it might have actually accounted for more of dark matter, or it
Yeah.
could be that there was nothing there, and in fact, the mass is missing, but it's not dark matter and it's not baryonic; it's something else. So the possibilities were still really open on what was causing this missing mass in the universe.
Yeah, it put a really big sort of cloud over the current lambda CDM model that there was so much of this regular baryonic matter that we could not account for. And so a lot of proponents of modified gravity sort of still had a really big leg to stand on because there was such a huge cloud of doubt over it. Now, hopefully, this sort of brings everything together, solves the problem, fills in the holes.
And it's exciting for people who've been interested in this unexplored time domain in radio astronomy. Typically, with our radio telescopes, we can look at small bits of sky, or any telescope, we can look at small bits of sky at any given time. We're not seeing the whole sky all the time. And if we are, we're getting so much data, like Kimberly said, we see the bursts, months later once we finally get through the data. So this time domain, these variable sources are not well understood. That's why they have the name fast radio bursts. It bursts in radio and it's over quickly. That's all we know about it.
Yeah.
So this is a project for upcoming big radio telescopes and big arrays to be able to monitor the whole sky in real time. So I wasn't necessarily expecting Parks to come up with this so quickly, but they did, and it totally kicks butt.
Now, have you got everybody in your one of your classes to fix their textbook?
Actually, I don't have a textbook for my intro astronomy course. I'm assigning them online readings.
Yeah, but you should. You should we all take the book. We all just edit it.
Yeah.
As you had to do when there were 9 planets. Like, oh, there's only 8 now. Yeah.
I have a quick question for Kim.
Yeah.
Is it possible that this fast radio pulse is caused by an alien megastructure orbiting around a star?
Come on, Jolene, really? Oh.
No, you took the words right out of my mouth.
Right there.
People. Never gonna let me let it go.
Nicole, I got one question for you here.
We're talking about SETI in my class. Why not?
Yeah.
But,
Jake Hooft asks, are FRBs directional?
Oh.
Could you get some science from light echo studies? So could you see stuff from the bursts bouncing off other stuff around them?
I don't know much about radio light echoes.
I don't either.
I don't think we know if they're directional or not.
Yeah, because we'd only see them if they pass by us. And one of the tricky things is that very few fast radio burst signals actually match another fast radio burst signal, and so there could potentially be many different ways to produce them, some of which might be directional and some not. So I don't know if that answers the question or not, but
yeah.
Okay. All right. Well, so when people are talking about gravitational waves, remind them that we now know what half of the mass is, the half of the baryonic matter in the universe is, and that it's as important discovery.
Yeah. For all those dark energy, dark matter conspiracy theorists.
They'll find the evidence overwhelming, and they will collapse.
Sure.
Gratefully. Yeah. Okay, let's move on. Jolene, talk about how, oh my God, NASA's figured out a way to get probes to Mars in just 3 days.
Yeah, super, super exciting. We're totally going to be there next week sometime. Not quite. But the thing here, though, is that the difference with sort of this thing, which it's called Deepen, and basically what it is it's using lasers to travel through space in a similar way that light sail operates. But the difference between this tech, which could theoretically be used to get us to other alien planets and alien solar systems, is that the technology exists. The problem that we have is an engineering problem, not a physics problem. So if we're talking about warp drive, EM drive, things like that, we're talking about breaking the fundamental physics that governs our universe. This Deepen project, though, the technology actually exists and it could theoretically work. Basically, what it is we would put a orbiting solar array going around the Earth, and we would use this array to fire pulses of lasers at a really, really large, ideally, sail and this sail, it would use those lasers to be propelled to excessive speeds. The thing with lasers, because it operates very, very similar to the light sail, as I said, is that 99.9% of the light is going to be redirected. It's not going to be observed. It's going to be reflected. So that works a bit better. However, in relation to this array, in order for it to be scaled up so that we could propel objects of a meaningful size, so something that's smaller than, tiny centimeter or millimeter objects, the array would have to be about 100 square kilometers in size. So it would have to be mammoth, which is obviously beyond our technological capabilities right now. So that laser array that could theoretically hit the device and propel it through space would just need to be huge. Also, there's issues with trying to ensure we can direct the lasers to run in parallel and hit at the same time to ensure that it's actually hitting the sail on this object we're trying to propel. And then there's also issues with steering the thing. So even if we could build this huge array, and even if we could direct the lasers so that it hit the object, the sail, properly, where would it go? It would be very, very difficult to steer. Also, the sail would have to be super, super thin, really thin material. And although space is kind of mostly empty, we don't see lots and lots of dust particles or small rocks. Because it's going to be so wafer thin that if it did encounter dust, it would spell kind of doom for the device. So we're not talking about getting to Mars in 3 days anytime soon. This type of technology is like long, long ways off, but theoretically it could actually work. So worth pursuing, but...
Right. So just to be clear about sort of what they're proposing is that, as you said, some array of lasers maybe orbit around Earth, or maybe even sort of in various orbits, so they line up and can provide acceleration, and then they zot this solar sail spacecraft and give it more and more kicks so that it can just get faster and faster and faster.
It keeps going faster and faster. Exactly.
Yeah.
And the interesting.
One of the downsides, of course, is how you slow back down. But I guess you probably could just do another aerodynamic braking, just really, really carefully when you come into the orbit of Mars, or zap it with lasers and orbit at Mars to slow it back down again to decelerate it when it's arriving at Mars.
What would be super cool, and what the sort of the plan is, of course, is not just to try and build this whole huge, massive array, but to do it in stages. So Philip Lubin is actually the individual who, he's an astronomer and cosmologist who was talking about this. He just did a conference and released a video. That's why it's sort of in the news this week, because we're already doing this just on really, really small scales, using lasers to propel molecules, or not molecules, but like light and different things like that, small things to excessive speeds, is that we could scale these down and use it to test out on, say, they were talking about using it for asteroid deflection, stuff like that, and that type of stuff that actually is viable that we really could build would prove a concept for perhaps this later, more mammoth and intricate technology.
Yeah, and then you can kind of imagine some future method. I mean, this is the only feasible method of doing interstellar travel that I've ever sort of seen described, where you build this big, long, almost like accelerating track in the solar system, and then you wait until all of these lasers are all nicely lined up, and then you take your probe and you just have it run down this track, and as it gets out, each laser is trying to accelerate it more and more and more until it gets, until it's moving at some significant fraction of the speed of light, and then it can actually make it to a nearby star within our lifetime. So, maybe it's only going to take 100 years, but at least it's not 100,000. So it's a really interesting technology. I mean, all of this stuff, right? I mean, the solar sails, using lasers to accelerate solar sails and slow them down. It's a wide open field, and we really should put a lot more work into it. So I'm really glad that NASA is talking about it. Planetary Society is talking about solar sails. So there's a lot of really interesting projects in this field. Yeah. So let's just watch and see what happens. But I'm excited. I'm stoked. Was there a question here? There was a question. Someone wanted to know. Oh, go ahead, David.
I think there's going to be another nanosail flight with the Falcon Heavy test this April, I believe. Is one of the payloads going up with that. So they're going to be doing another nanosail flight.
Yeah, I mean, you can even imagine like solar sails as an inexpensive way to get cargo slowly to Mars. Like I'm sure Elon Musk has a team doing the math on solar sails because they make a lot of sense.
Yeah, the main thing is, so we use chemical propulsion now, which of course is a lot of very expensive, not terribly sustainable for the planet, and so using stuff in the electromagnetic spectrum, which is obviously renewable, would be 1,000 times better. If not,
yeah, you can imagine these big lasers just sitting around with big batteries soaking up the sun, and then when they're ready, they just go zut, and they can. You imagine some future civilization has hundreds of them positioned around the solar system, and you just catch
optical SETI.
Yeah.
Maybe we'll see their laser bursts out there as they're doing this sort of transport.
Yeah. Nancy Graziano says Mark Watney can't wait for supplies to get there slowly. That's true. So they need the fast version to get to Watney. All right, let's move on. So, David, why don't we talk about WFIRST?
Yeah, last week, it was right around last Friday. I didn't get to writing about it on Sky and Telescope till this week. NASA announced that they are formally beginning work on the next generation space telescope after James Webb, the Wide Field Infrared Space Telescope. And this actually has an interesting backstory that we wrote about a few years ago. This is one of the Hubble-class mirrors, one of two that was donated by the National Reconnaissance Office to NASA because they just have mirrors, 2.4 meter mirrors laying around apparently that they don't need. And NASA decided that one of the mirrors is going to be the WFIRST telescope, set to launch probably, we're seeing right now maybe 2022 right now or so. But this one is going to also go out to the same Lagrange point, the L2 point, as James Webb, which is launching next year, I think. It's 2016 now. I believe it's 2017, 2018. They're going to be putting Webb up. But this is going to differ from Webb. This is a single mirror, like Hubble, and it also has a very fast focal length, which gives it a wide field of view. That's one of the key things with this telescope. It's going to be an infrared telescope, 100 times the field of view of Hubble or James Webb. And I actually had to do a lot of digging and actually interview one of the researchers to find out. I watched the talk on this, and why it's got a wide field of view is because this fast focal length is just like an amateur scope. The shorter focal length you have, the wider field of view you have. But actually, numerically, how fast it was, it's in the field of an F7, which building telescopes, it's fast, but it's not like Large Synoptic Survey Telescope fast, but it's going to give it a much wider field of view. Compared to Hubble, I believe Hubble is like an F18 in that range. So for people that know f-stop and things like that, it's the same as we have in photography and telescopes.
So what would you use then a wide field infrared telescope for?
Well, this is going to have a chronograph, similar. It's going to have a high-definition chronograph, one of the first ones they've flown, which means it's going to be able to block out starlight and look for exoplanets, directly image exoplanets near. James Webb is it's NIRCam, I believe, is going to have a chronograph on it too. But this is going to be a high-definition chronograph. They're going to be looking at a lot of other things like just infrared survey type, There's a big thing out there right now about trying to find Planet 9, and as infrared telescope might play into that. And incidentally, there is another idea beyond the next space telescope, beyond WFIRST. It's what's called the high definition space telescope for the 2030s. This is going to be like James Webb with a segmented mirror that's going to have to fold up. The problem you get with really big mirrors on putting them on rockets is you still have to fit it inside what we have for a launch vehicle to get up there. So if the launch vehicle is the SLS or an Atlas V or things like that, or the space shuttle, when we had the space shuttle, you still have to fit that in what they say, here's the cylindrical area that mirror has to fit in. So if you want a mirror bigger than that cylindrical area, it has to fold up like James Webb and deploy. So until we can get anything bigger than SLS, which is supposed to test launch, I believe, 2018, that's going to pretty much determine the size of these kind of payloads we can put up there.
Well, I wonder what the fairing size of the Falcon Heavy is going to be. How big?
I don't know if it's going to be bigger than SLS or not. Which they're supposed to test launch Falcon Heavy this year.
Yeah,
of course,
so that's going to happen sooner.
I write about space stories. It's interesting. I look back and see space stories to watch in the coming year for New Year's, like for the past couple of years, and we've been chasing this Falcon Heavy launch date like almost every year. So, but it seems like they're actually coming around to, April it's almost March now. So I believe it's going from Vandenberg.
What a time! Like James Webb, the Large Synoptic Survey.
Yeah.
Ideally the Magellan Telescope, some of the radio observatories, the Large Square Kilometer Array, the gravitational wave detectors. Like, we're just getting started. The coronagraphs. What a good time.
And this is going to generate beyond terabytes of information. That it also is going to be something. And if they make this all publicly available, this is going to be something that amateurs are going to be combing through, looking for near-Earth objects, comets, like everything. Like when they put SOHO up there, and now amateurs sit and find sun-grazing comets.
Yeah.
It's kind of cool when that's one of the first things that drew me into the web back in the 90s, initially, when I heard that there are people out there discovering comets on the internet, that don't even own telescopes. It's like, that's cool.
Lars Rye Jepson asks, so what happens if the rocket carrying the James Webb Telescope explodes? Is there a copy of it laying around? No, there isn't.
And I would hate to be that range safety officer that has to make that decision to push the button on that. I really wouldn't want to have his job.
Yeah, it's a $5 billion self-destruct button that you have to press.
Yeah. Yeah.
All of astronomy will weep.
Yeah.
There'll be a great crying out across the cosmos.
Yeah. As if a million astronomers were crying out.
I was going to say a million telescopes just went silent, but beat me to it.
Yeah. Okay, so Nicole, why don't we talk about gravitational waves and pulsars?
Yeah. So on the heels of the gravitational wave discovery, there was a paper that was actually submitted before the discovery, but just came out about a method for discovering or for looking for gravitational waves using pulsars. So pulsars are these super compact dead remnants of stars, and they'll have a hot spot on them, then they're rotating, so it flashes like a lighthouse, often detected in radio. And by getting the precise timing of those flashes, you can learn things about the pulsar or about stuff happening to the pulsar. In fact, one of the first exoplanets was discovered around a pulsar because the gravitational tug made those flashes come at a different time than we expected. But by using an array of pulsars, so observing an array of pulsars, astronomers are hoping to detect gravitational waves. As the gravitational waves go through this array of pulsars, it'll change the timing just so. And now sometimes people are like, oh, well, we've discovered gravitational waves. Why do we need to keep discovering them different ways? That'd be like saying, well, we discovered visible light. We don't need any other kinds of light. What's this all about? Because these are going to be sensitive to long wavelength gravitational waves. So from a different class of phenomenon or a different stage of the black hole merger would be seen by this. So there's a couple of collaborations. One in particular put out the study called NanoGrav. It's the North American Nanohertz Observatory for Gravitational Waves. Nanohertz is the very, very tiny frequency or very long wavelength of the gravitational waves that they're trying to see. So they put out a study recently. There's been some discussion in the literature about we've been doing this pulsar timing for so long and we haven't discovered gravitational waves this way. Is there something wrong? Is this not going to be feasible? But it depends on what assumptions you make about how black holes collide. We don't know all the mechanics of how these supermassive black holes collide, as well as being able to pick the right group of pulsars with the right spacings, with the right timing that you can actually tell. So they're saying that they still think they're just a few years off from making this discovery of these long wavelength gravitational waves from these, using these pulsars. So using the pulsars as the telescope, sort of, right? These are the sources that we're watching wiggle around, but then using radio telescopes like the Green Bank telescope, for example, in West Virginia, to actually get the timing just right on those, to actually detect the radio waves from these pulsars.
Yeah, I mean, the great thing about pulsars, right, they knew that the gravitational waves existed thanks to pulsars back in the 70s. Like, they won a Nobel Prize for this.
Yeah.
So, finally taking whatever 30 years to confirm it with this other method is great. But the pulsars are still your best method, your cheapest, best method to find these gravitational waves. So.
Right.
Oh no, Kimberly's got to go plug in her laptop. So we're gonna move on back around to. I guess we'll talk to Jolene again, and let's talk about Scott Kelly being in space for almost a year. Is it already almost a year?
I know. It seems like just yesterday I was reading an article about how, hey, he's going to space, and now he's coming back. So Scott Kelly has been in space in the ISS for about a year now. And he's actually coming back this coming week. So March 1st, he's going to be back on Tuesday of this coming week. And he was doing a lot of things up there. Obviously, they do tons and tons of tests on the International Space Station in relation to how different organisms respond to zero-G, very little or next to no gravitational force. Also growing plants and doing all sorts of different stuff like that. But why send up one person to stay for an entire year? And the ultimate reason is that if we're ever going to travel through space for an extended period, we need to know how the human body reacts. So Kelly said recently, one of the interesting things he noted in a Reddit AMA is that the calluses on the bottom of your feet fall off when you're in space because you're not walking around. The tops of your toes actually get calluses because you use those to keep yourself in place and propel around a lot. That's not going to be life-altering or really terribly body-altering. But one of the things about zero-G is that it impacts your bone density. So do you have significant bone loss when you're in space for extended periods? How does your microbiome? I mean, so we're all made up of billions and billions of different bacteria that keep us healthy, make our immune system work, and so on and so on. How does that respond in space where the environment is a lot more sterile? We don't encounter the same bacteria that we do here on Earth. And what made Kelly the perfect candidate for this, to see how the human body reacts in extended periods of space, is that he has a twin. So we have two people. We can compare one to the other because his brother, I have it written down, what's his name? Anyone know off the top of their head? Mark Kelly.
Also an astronaut.
He is, yes.
Yeah.
He's retired, so he's on Earth. And so we can look at Scott, who's in space, and Mark, who's not in space, and compare their two bodies, look at the psychological impacts, and basically do a whole analysis of the different changes and have a better understanding of the human body in space, which, we were talking a lot the past couple of hangouts about going to Mars and doing all that fantasticalness. But even if we do manage to get there in 3 days, thanks to this super awesome laser technology, I imagine we'll want to stay there for a bit. Knowing how the human body reacts in different forms of gravity, because of course Mars has a lot less gravity than the Earth does, or at least a bit less. It's not the exact same. So that's why he was in space for a year. The end.
And he is just taking the best pictures.
Oh, the gorilla thing?
Well, the gorilla thing was great. But, I mean, if you have to check this out, he had a gorilla suit sent up in a resupply mission, and so he freaked out his astronaut cohorts with this.
I always wondered where we would finally find Bigfoot. I did not expect it to be aboard the International Space Station.
Yeah,
not see that one coming. No.
Yeah. Bigfoot is definitely a space traveler. But like just his pictures. Like if you look at the pictures that are on like again NASA. We talked about this last week. How good NASA is at social media, and a big part of it is they have the people on the scene, right? They have the astronaut taking the pictures from space. And they know how to, get them out there really well. So if you're not on Scott's Instagram or on his Twitter, oh, it's so good. All right, let's move on. Now that you're back, Kimberly, let's talk about Planet 9.
Yeah, sorry, I had to run away for a few seconds. But Planet 9, if you recall, about a month ago or so, Planet 9 hit the news with a big splash. Astronomers said that they had evidence that there is possibly a rather large planet orbiting very, very far in our solar system. They have not seen it, and they don't think that they're going to see it, but there is a lot of evidence that's saying that there should be something there based on the orbits of some other objects out in the Kuiper Belt. Well, a little bit of an update on that. That helps sort of solve the problem of how could we ever hope to see this thing when we don't even know where to look. Well, another group of astronomers have devised a rather clever way of sort of narrowing down the field of where we need to look if we want to see if Planet 9 is really there. And what they've done is they've realized that if there is a rather large planet orbiting distant in the solar system, it's not only going to affect the orbits of Kuiper Belt objects, but also of the other 8 planets in the solar system as well. And so what they did is they took data from the Cassini mission, which has been orbiting Saturn for quite a number of years, and they've compared the measured position of Saturn over the past many, many years to the predicted positions of Saturn based on just orbital dynamics and regular physics. And when you compare the predicted positions of Saturn to the actual measured positions of Saturn as measured by Cassini, what you can do is you can figure out where Planet 9 has to be in order to make up the difference between the two. And so what they've done is they've actually narrowed down the entirety of Planet 9's hypothetical orbit to a rather small little swatch of a probable position and a quite larger area of possible position. But even more excitingly, they have ruled out a good fraction of the orbit as completely impossible to produce the effects that they're seeing, not only on Kuiper Belt objects, but on Saturn as well. So we still haven't seen it, but it starts to chip away at one of the big barriers towards actually discovering if Planet 9 is there by sort of narrowing down the field of where we need to look, which is exciting. I hope we can keep narrowing.
I'm trying to find the. I've got the picture. I'm going to try and share it.
Oh, it's just getting that. Do you have
Racia.
Yeah. Oh, the orbit. Yep, there you go. Yeah, so Planet 9, there's that small green triangle there. That's the probable zone of the most likely place that Planet 9 needs to be right now in order to affect Saturn's orbit in the way we think it does. The 2 red swatches, those are excluded zones where Planet 9 definitely shouldn't be. And anywhere that's not highlighted is still possible, but it's not completely ruled out, but a lot less likely than that green area. So let's.
Do you have any idea what type of distances we're talking about? I mean,
at this distance, it's still probably about 10 to 15 times as far as Neptune.
And it's probably, what, bigger than Neptune, right?
It's probably bigger than Neptune, but so far out, and having no idea what the composition would be, we don't know how much light it would be reflecting. It's probably very, very dim even still. So we really need to have a good idea of where it is if we want to actually focus our telescopes on it, because we would need to image that thing for a very long time in order to collect enough lights. So it's good that we're narrowing down the field.
Yeah, well, and it's just a matter of getting time on, for example, say WFIRST to zoom in on that region and look for an object in that period. Or things like the Large Synoptic Survey Telescope is going to turn up. It's going to turn up dozens of objects. It's going to be amazing once it. I know, I go on and on and on about it. We should get somebody from the LSST project here on the show.
We should.
Okay.
I
just put that out into the universe, and I'm sure the universe will respond.
I'm kind of curious to see if he'll see it before my class ends this semester. That would be interesting.
Planet 9?
Planet 9 for beginning to end in one semester.
Yeah. Yeah, and then, then it'll be great. It's like all the Planet X people. We can go, yeah, I know, it's right there. It's right there. Let's watch it. No, still not coming close to the planet. Still not flipping our poles or starting a new time of Age of Aquarius-ness. Okay, let's move on. Dave Dickinson, let's talk about Shadow Transit season.
Yeah, we're
already.
We're approaching opposition season here for Jupiter coming up, and we've actually got a special treat in that we've got a series of double shadow transits where you've got 2 of the large Galilean moons transiting at once. There was quite a few this year because I look through these when I do my 101 events for the year, And somebody did point out, it's like, there are 27 of those are double shadow transits alone. And I was like, yeah, there seems to be more than usual. And actually, that's because we just passed plane crossing season where we're crossing the ecliptic plane. The ecliptic plane is crossing the orbital plane of Jupiter's moons last year. All the moons can shadow transit except Callisto is the only one, the outermost of the 4 Galilean moons, that can occasionally miss. And it's wrapping up its season of shadow transits in July of this year. We're going to have the final one, and then it's going to wrap up until 2019, I believe. But I listed the ones that are targeting for North America. Actually, I found an interesting photo. I dug around to see if any had been captured from space. See if I can screen share this. I had never seen this till I researched this. This is from New Horizons when it flew by Jupiter back in, I think it was 2007, 2006. It flew by Jupiter, and actually you can see a notch of one of the moons up there at the very edge, because I was wondering if a double shadow transit had ever been caught from space before. The only spacecraft that's orbited Jupiter is Galileo. Until this summer anyway, we're going to have the Juno spacecraft orbiting as well. But New Horizons visited, the Voyagers, the Pioneers visited, all for gravitational assists. And so there actually has been a double shadow transit. You can see these kind of events even with a small telescope. Probably a 6-inch Newtonian would probably be the ideal minimum. You can see a shadow transit in smaller instruments, but they're not really apparent unless you get something 6-inch or bigger.
I really like the bookmarks that you have on your,
I know.
browser there.
That is the only way I could get it to screen share. I was experimenting with it there earlier.
Yeah, I couldn't get my image to screen share either. Maybe on Windows.
Yeah.
So just for people to remember that they can see planets with their own eyeballs. If you're out in the morning, what can you see? And if you're out in the evening, what can you see?
Well, right now the evening is pretty empty of planets, but Jupiter is moving into the evening sky here come March. All the planets are in the morning sky. Venus is kind of moving off, but it's still visible in the morning. Mercury, of course, broke the lineup where all the planets are. That's going on the other side of the sun now. And incidentally, Mercury is going to be transiting the sun next time it comes around. It's in early, I think it's May 9th, without having anything in front of my eyeballs here, but it's going to be transiting the sun. That's going to be something to watch for. Mars and Saturn are in the morning sky near Quadrature. We talk about their 90 degrees west of the sun right now. Mars is going toward a very good opposition coming up too this spring. So Mars, we're going to, after we end up Jupiter opposition season, we're going to be focusing toward Mars opposition season.
Well, Jupiter's up in the evening for me now. I'm seeing it around 9 o'clock, 10 o'clock at night.
Yeah, it's not up high, I guess I could say, until like midnight or so right now. But it's going to be reaching opposition. I don't think of them going really into the evening sky until they cross opposition.
Yeah, but if you're seeing that really bright,
7 to 9 because that's when my lab is scheduled. And there's been no planets.
But it'll be momentarily. Like if you look off to the east, you could definitely see it there in the evening.
Yeah,
it's that bright star. Get a pair of binoculars, take a look at it, and you should see the moons.
I had some students come out. I had an extra credit assignment where they could come out with me at 5 a.m. to see all 5 planets, and several of them took me up on that offer. It was really nice.
Wow.
They got it just for Mercury. Yeah, they got extra credit for coming out and looking at the two telescopes.
Lillian Brennan wants to know, will Mercury's transit be anywhere as visible as Venus's?
It's going to be smaller, but you will be able to see it. Like if you have a pair of, you'll probably need like a small filtered telescope. I observed the one in 2006. I had a filtered telescope. I did a public outreach event at the Flandreau Observatory in Tucson. That's the only other than the 2012 one of Venus that I've seen. But if you've got one, if you got like a little PST that can observe the sun in hydrogen alpha, you'll be able to see it. The disk is going to be much tinier, of course, but it's one of the rarer events. I believe we have one in 2019. Mercury generally transits roughly once a decade or so. It's much more frequent than Venus because it's got a faster orbit and closer in, but it's kind of neat to see.
It's the day of my astronomy final, my Astro 101 final. So it'll be too late to offer extra credit.
Extra credit. Well, like, maybe you could do it while the final is happening, though.
Oh,
There
yeah,
you go.
there you go.
The final begins when the transit begins, and the final ends when the transit ends.
Oh,
There you go.
I just looked it up. It's a 7.5-hour transit.
Perfect. Give them
Yeah.
7.5 hours.
It's evil. Oh gosh.
That's
Yeah.
like a qualifying exam.
Yeah, you have 7.5
students.
hours, and if you don't finish by the time Mercury leaves the disk of the sun, you failed.
I think I was courting heat stroke, the one in Tucson that I did, because I was out manning the telescope, and of course you're under the sun in Arizona, and it was a rather, even in November I think it can still be pretty hot there, so it was a fun event though.
Nicole,
Yes.
let's talk about a survey of gas and dust.
Oh, yeah. There was
Milky
a cool map that was called Atlas Gal. I'm going to see if I can screen share this baby. It's a map that was completed by one of the sub-millimeter telescopes out in Chile called APEX.
It's pretty.
The Atacama Pathfinder Experiment Telescope. So it's in the Atacama region of Chile. It's a single dish telescope looking at sub-millimeter wavelengths and looking at gas and dust. That is some of the coldest gas and dust in our galaxy, so 10, 20 degrees above absolute zero. And so they released this really pretty image showing all of the Milky Way that is accessible to the southern hemisphere. You can see on the right of this image, it even shows the range of the disk that is shown, and you can see all kinds of cool features. Some of the more circular features are probably from supernovae. So it's just some insights into high mass star formation, clusters, the evolution of stars in our Milky Way galaxy. So I wanted to show a pretty radio/sub-millimeter image from APEX.
I apologize to all the people who are listening to this as a podcast, if you're driving or whatever. Nicole just shared an amazingly stunning view of the Milky Way seen edgewise. And you know what's kind of funny is how, if you looked at those three lines,
Yeah.
You wouldn't know which of those lines contains the core of the galaxy very easily. You
Right.
probably have a guess at it, but you would think that what is the center of the galaxy and what is off in the outskirts would be really super obvious which is which. But it's
Depends
actually
on, it totally depends on what wavelength you're looking at. We can
Yeah.
see this cold gas and dust in every direction, and there's a little bit of I guess they chose a redder color and some brightening around where the galactic center is. But you're right, it's not completely obvious just by brightness where the galactic center is.
yeah. Okay, so last but not least, this week in Musk, if we should have been congratulating SpaceX on a successful launch yesterday.
Yeah, I think they actually delayed from Wednesday. There was a lot of wacky weather that came across the East Coast and the Space Coast too, and they delayed because of weather on Wednesday, and then last night they nearly got off and they canceled. I think they were at T-2 minutes when I was actually watching it here on I had the Fire Stick at SpaceX, their YouTube channel fired up here at the hotel building, and I was watching it, and I believe it was for a fuel flow problem. I kind of only caught a little bit of, there was a lot of conjecture of what it was, but it was obvious that it wasn't anything they could fix in the hour-plus long launch window they had. The satellite they're trying to launch is SES-9, is geosynchronous, bound for geosynchronous orbit, communication satellite from SA Luxembourg is the owner of that they were trying to put up. And they were going to try to do the landing on the barge again, which they've never done yet. They did a landing last, was it December, on land, but they have yet to actually land and stay upright every time they've hit the barge.
It did
What I'm
land,
seeing on
like half
Hard.
a fraction of a second. Yeah, it was like, it was so painful to watch.
then
Slow motion
it
came
timbered
over.
up. It makes some awesome videos though when it explodes. It's kind of cool. I'm looking at spaceflight now. They're saying there was a lot of conjecture before I came on the Space Hangout about when the next launch attempt is going to be. Spaceflight now is saying 2 hours ago, sources say Falcon 9 launch attempt no earlier than Sunday at 6:49, no earlier than 6:47 p.m. Eastern Standard Time. So we'll see. I know it's a whether they can get the range constraints and they can get time on the range. And I know from working aircraft, if rockets are anything like when you have a fuel problem, it's not something you can fix quick because you've got to defuel and then troubleshoot and then refuel. And I believe it was related to that as why they couldn't make the window last night. So we'll see Sunday night if they go.
Well, don't take any chances.
Oh, and those evening flights, those are during twilight hours in Florida, because I lived down there for several years. Those are the coolest ones to watch, especially early morning. But evening in the PM is kind of cool too, because they are visible from over 100 miles away. So if you live in Florida and your skies are clear Sunday night, I would definitely get out there and watch.
Oh, I wish. That'd be awesome. Well, I think we're sort of reaching the end of the show. A bunch of people are in the chat. We're talking about the Voyager probes and sort of an update on the Voyager probes. So maybe we can find a guest who talks to Voyager and maybe come on the show. Hint, hint. And the reason I'm hinting, and I actually have no control over this, is because I want to sort of now do a big pitch to the people at the Weekly Space Hangout Crew. These are, of course, really the executive producers of the show, hundreds and hundreds of people who come together, talk about the show, suggest guests, and then they go out and find the guests and have them come up on the show and help us find stories that we want to talk about. So we really couldn't do the show without their help, and I want to, as always, give them a huge thank you and more encouragement. So if you want to join a really great community that is really a part of the show itself, like I'm telling you, it is not your standard place where you go and chat. Like, they'll put you to work, but you'll be able to make the content that you want to see here on the show. I am just a meat puppet who does what you need. They are the ones who do actually organize and coordinate and make the show happen. So thanks to them. Just do a search for WSH Crew, and you can find that great group of people, both their website, their various communities on various social media, and participate. So let's give people a chance to shamelessly self-promote things that they're working on. So, David, where can we find out more about you?
See, this week I was active on my own site, AstroGuys with a Z. I'm AstroGuys with a Z on Twitter. Universe Today, of course, Sky and Telescope, Listosaur. I have my author page over on Amazon as David Dickinson. There's, I believe I'm going to have another story up there. It's in the final stages next week. And, I'm on Instagram too, so check me out.
And I think, if people haven't already, they should have bookmarked on their browser bar your 2016 guide for what to see in the night sky for,
Hey, I'm already working on 2017, so it's a...
You make my teaching easier. You have no idea. I have to do
It is,
jobs.
yeah, I think it's one of the most important sort of astronomy guides that comes out every year. So you're just an absolute gentleman for creating it, and I'm really honored to be able to host it on Universe Today. It's such a treat to have.
It may be an ebook one day. It's growing every year. So
let's talk, David. I would be glad to help you publish that in some kind of format. So let's figure that out. Let's do it. There, you just saw a deal get done. Jolene, where do people find out more?
You can go to futurism.com or the Facebook page, which is also Futurism, or the Twitter, which is also Futurism, Instagram, also Futurism. You notice the trend there.
Now, we are working on a collaboration, so you posted to your community to have people send questions in for me that I'm then going to make a video about.
Yes, there's space and astronomy questions or physics, or we got a bunch of different stuff.
So are we done? Can people sneak in some more questions, or are we out of time on that?
If people want to, yeah. I mean, there's no... we had said like 24 hours definitely, and then it's been up for like a week. So
yeah, okay. Well, then never mind. You're gonna have to wait for my answers. Okay. Kimberly, where do people find out more?
People can find out more by following me on Twitter at AstroKimCartier, by visiting my website, KimberlyCartier.org, and of course every week here on Weekly Space Hangout.
Yay!
Yay, Weekly Space Hangout.
Cool. And Nicole, where do we find out more?
I'm much harder to find on the internet these days, but I'm around. I'm Noisy Astronomer. Twitter. I don't really do much else right now except surviving first year. # first year prof. So.
But let's say that we wanted.
You're in New England.
Let's say if we wanted to have you be our professor.
Yes.
How could we do this?
Well, you'd be a student at St. Anselm College in Manchester, New Hampshire. Yes,
And
I'm
then
teaching.
take.
Well, I'm teaching this semester. I'm teaching Introduction to Astronomy, and Life Beyond Earth. One of my favorite courses to teach. The next semester, what am I doing? Modern physics, so I get the physics majors again, and so I'm developing a solar system course. So actually, I'm trying to develop an astronomy minor on our way to developing an astronomy major. So, starting all the cool stuff.
You gave me one of the most interesting kind of sort of thought processes about searching for life outside the Earth. I don't know if you're aware. You mentioned sort of offhand one time. Well, you know that the aliens have been watching us for 500 million years, right? Because any alien civilization with the right technology would have the ability to detect the gases of life, cow farts and combustion engines and all that kind of stuff from afar. And so any aliens out there would know with great certainty that there's life here on Earth, and in fact would have watched it move through. And so, there's no way the aliens don't know that we're here. They know we're here.
So where
are they, right?
Yeah.
So if they're there and they know that we're not here, and they would know that we would probably be trying to communicate with radio signals, they would have sent some kind of message to Earth. So
or they realize that we're jerks and they don't want anything to do with us. That's
or they've sent the Vogon constructor fleet, and it's just a matter of time before it arrives. But the fact is, like, if you think that we can hide, there's no way. They know. They for sure know we're here. And I think you hit the nail right on the head, which is like, we don't have to worry about sending signals with our radio dishes.
We're doing it. I remember saying that. Probably, some prominent astrophysicist probably said we shouldn't be sending signals into space. It's like,
yeah, we've been broadcasting our existence for 500 million years. Thanks, bacteria. Thanks for letting the secret out.
Oxygen.
Yeah. Thanks, phytoplankton jerks.
There's yeah, actually, I make my students write essays on this kind of stuff all the time this semester.
It is the most powerful problem as part of the Fermi paradox for me that just takes my brain and just kind of goes, done. We're the only people and we're the only life forms in the universe, and it's all really sad. So anyway, thank you for sticking that virus in my brain.
Yay!
And I use that as sort of one of the keystones of my argument about the Fermi paradox, and I've done it a bunch of videos, and I stole it shamelessly from you. So thank you.
I'm sure I stole it shamelessly from watching Contact. So it's
I will deny all knowledge.
There's a
cool.
question about any web-based courses. They just started doing online courses here, so I'm not teaching anything that's available online. I did used to teach through CosmoQuest and Cosmo Academy, so they occasionally do some really great online courses at CosmoQuest. I don't know if they're still doing that, but that's a possibility.
Go to Cosmo Academy, and you can see the courses that are running. Although
so I did a couple of those, but I'm not doing that because I am trying to keep my stuff together.
Good luck with that. Okay, cool. So just to remind everybody, if you haven't already, like this video on the video page, subscribe to this channel, and then go the extra step and force YouTube to send you all kinds of notifications when our events go live. And that way, your phone will freak out when we're about to do a live show, and it'll go into your calendar, and your mom will call you and remind you that it's time to watch your Weekly Space Hangout. So take that extra step. Thanks, everyone. Thanks to the crew for supporting the show. Thanks to our panel for showing up and bringing the news and the science. Thanks to have Nicole back. Don't be a stranger, Nicole.
Guys. I'm trying. Spring break gives me a little bit of breathing room in my class prep and grading, so I can do a few fun things.
Well, we're honored that you chose this to do that. And Dave, good luck with your flight. I hope the next time we talk to you, you'll be in Spain.
We'll be in Spain, Wi-Fi willing. I'll be with you guys.
That sounds great. All right, thanks everyone. We'll see you all next week.
Bye.